So having looked at those enthalpy changes for the previous reactions, I want us to continue from today onwards, looking at the average bond energy and very many other enthalpy changes that will end this topic. Benjamin, are you there?
Yes, I'm there, teacher.
How about Ali?
I'm present, sir.
Okay. Now, for any polyatomic molecule of this formula, this molecule here, let me get my pen. Molecule you see here is assumed to have a structure of this kind. It's assumed to have 3 bonds, where in each of the 3 bonds it is bonded, the A is bonded to X. Are you getting me?
Yes, sir.
There are 3 bonds,
Yes.
where the A is bonded to the X. Are we together?
Yes.
Now, it has 3 A to X bond energies. This is what we mean. There are 3 A to X bonds. Now, to get the average bond energy of such a bond, we divide the bond energy of the 3 A to X bonds by 3. And that's why we are saying that the average bond enthalpy of such a compound is 1/3 of the enthalpy change of this process. You get what we mean?
No.
You haven't got it yet.
Yes.
Okay, if you haven't got it yet, let me look at methane. When you look at the compound methane, methane has the formula CH4. Methane
Yes.
has the formula CH4. As you see here, this is the formula of methane. So if I want the average bond energy of methane, I should be aware that in methane there are 4 carbon to hydrogen bonds. There is 1 carbon hydrogen bond there. There is another one. There is another one. And there is another one. So if we talk of the average bond energy of methane, we mean the average of the bond energies, which are 4 here. So the total bond energy of methane will be 4 into the bond energy of, to be 4 into the bond energy of 1 carbon hydrogen bond. So this is what I mean. If I talk about bond energy of methane, it will be 4 multiplied by each carbon hydrogen bond. Are we together?
Yes.
So this is what we mean in this statement. If I say average bond energy of the carbon hydrogen bond, It is the bond enthalpy of the whole of methane divided by 4 because methane has 4 carbon hydrogen bonds. Is it now more clear?
Yes.
Yes, sir.
So this is what we mean. This energy, we shall do a question where you have this bond energy, and then they ask you the average bond energy of the carbon hydrogen bond in methane. So it is divided by 4 because methane has 4 carbon hydrogen bonds. Okay. So the average bond energies are obtained from standard molar enthalpies of formation and molar enthalpies of atomization. And if the average bond enthalpy of one covalent bond in a molecule is known, then the average bond energy of the other can still be determined. Can I proceed?
Yes.
So we have this one here. We have this one. It says we are going to use bond energies to calculate enthalpy of a reaction. How do you use bond energies to calculate enthalpy of a given reaction? We use a general formula. Remember, in a reaction, some bonds are broken as others are what? Are formed, right? Are you aware of that, that during a chemical reaction, there are bonds broken and there are bonds being formed?
Yes, sir.
So if you are aware of that, then so if you are aware of that, then you should know that this equation is normally used in such calculations. Now, Frederick, can you read for us this paragraph?
Which one, sir?
This
The
one
screen
here.
has disappeared.
You're not seeing it.
The screen has disappeared.
Okay, let me see. Still, you're not seeing it.
Yes.
How does this come about? Even now?
Yeah.
Members, are you all not seeing the screen?
Teacher, me, I'm seeing.
I'm also seeing it.
What's happening with Frederick?
He should swipe to the left of his screen.
I think so. Now, Rima, can you read for us this paragraph?
Enthalpy of any given reaction can be obtained if the average bond enthalpies of the bonds involved are known. The
That's
relation.
really right. This is the equation we use if we are to determine enthalpy of a given reaction, given the bond enthalpies. So enthalpy of the reaction is given by summation of the bonds enthalpies of bonds broken. Is the summation of the bond enthalpies of bonds broken minus summation of the bond enthalpies of bonds formed, which we can write as this mathematically. This symbol here means summation of bond enthalpies of bonds formed minus summation of bond enthalpies of bonds formed. Summation of bond enthalpies of bonds broken minus summation of bond enthalpies of bonds formed. Is that formula clear to everyone?
Yes, sir.
Teacher.
I now proceed. Here is a question. The question says define the term standard enthalpy of atomization. Who can define that? Who remembers standard enthalpy of atomization by definition? Yes, Shamira.
Standard enthalpy of atomization is the enthalpy change that occurs when one element in its normal physical state is converted into 1 mole free gaseous atoms at 1 atmosphere at 298 kelvins.
It should be 1 mole of an element in its physical state. Okay?
Yes, teacher.
Is converted to the gaseous atom, to 1 mole of gaseous atoms, not the gaseous atom, 1 mole of gaseous atoms under standard conditions. Now you look at this question here.
Excuse me, sir.
Yes,
May you
Benjamin.
pardon me the definition?
Yes.
May you pardon me the definition?
I think I should take you back to that definition so that you can recall it. Are you here now?
Yes, sir.
I think you can read it yourself. Standard enthalpy of atomization. Read that definition. Is he here?
I've seen it, sir. This is the enthalpy change that occurs when an element is in its normal physical state, is converted into 1 mole free gaseous atoms at 1 atmosphere and 298 Kelvin.
Very good. The enthalpy change that occurs when an element in its normal physical state is converted into 1 mole of free gaseous atoms at standard temperature and pressure, or you can refer to a compound instead of an element.
Yes.
A compound in its normal physical state is converted into free gaseous atoms, 1 atmosphere and 298 Kelvin. Are we together?
Yes, sir.
So I can now proceed.
Yes.
So when I come back here, I think we had gone further behind. So here we have been saying we have this question and it's what we want to deal with. We are given bond enthalpies of different bonds and their bond energies, right? Just asking us to calculate standard enthalpy of atomization of methanol. Now here somebody, I think the best definition you could give could be that of a compound, because we are talking of a compound.
Yes.
Methanol. The enthalpy change that occurs when 1 mole of a compound, its normal physical state, is converted into 1 mole of, is converted into its free gaseous atoms. Here we shall not say 1 mole. It is 1 mole of an element of a compound now, converted into its free gaseous atoms under standard conditions, right?
Yes.
So if you want the enthalpy of atomization of methanol, we first write this equation to show atomization of methanol. Okay? So after writing the equation to show atomization of methanol, then we can see how we use these bond enthalpies to calculate the enthalpy change. Am I clear? So now how do we use the enthalpies how do we now use the bond enthalpies to calculate the enthalpy change for the reaction? This is what we do. What we do is to write this formula first. I mean the equation. Then try to break the equation into its separate bonds. Is everybody able to know where this comes from? Is everybody able to know where this is coming from?
Yes, teacher.
So the carbon here is bonded to 3 hydrogen atoms. Then it's bonded to 1 oxygen atom, which is also bonded to a hydrogen atom. So if I want an enthalpy change for atomization of methane, I will say that enthalpy change, because I'm using these bonds, is equal to summation of bonds broken, which are here, minus summation of the bond enthalpies of bonds formed. So the bonds broken here, we have 3 carbon hydrogen bonds. You see this, plus 1 carbon oxygen bond. We are now seeing these bonds and how many times they appear in this compound. So 3 carbon hydrogen bonds, 1 carbon oxygen bond, and 1 oxygen hydrogen bond. So we multiply the carbon hydrogen bond enthalpy by 3, as you see here. This is by 1, this is by 1 also, then minus 0. Why do I subtract by 0? Because these are not bonds, these are just atoms. Am I clear?
Pardon me, sir.
So this is the sum of the bonds that are broken. Is this clear with you?
Yes.
Now I have to subtract off the summation of the bonds formed. Do you see any bond being formed here? Is there any bond being formed here?
Yes.
Which bond do you see formed there?
The hydrogen bonds.
There are no hydrogen bonds because this is an atom. If it was this, then you would say there are hydrogen bonds being formed. This one is equal to 4 hydrogen bonds. That's what it would be. You get it?
Yes.
But in this case, it is just an atom. So this is not a bond, it's a hydrogen atom. Am I clear?
Meaning there are 4 atoms.
They are just 4 hydrogen atoms, not bonds, not hydrogen bonds. That's why these atoms, all of them, they have no bonds. We subtract minus 0. Is that clear?
Yes, sir.
Then you get your final answer. Can I proceed? The answer should have units as kilojoules per mole. Can I proceed, members?
You can proceed.
Yeah.
Here comes another question. Linda, can you read for us this question?
Write equation for the formation of steam. Part B, the enthalpy of formation of steam is negative 241.8 kilojoules per mole. The bond energies of some bonds are also given below. calculate the oxygen bond energy in oxygen.
Very good. So the first thing is to write equation for formation of steam. And it's here. This is the equation for formation of steam. I don't know what's happening here. So this is the equation. Remember, they said steam, not water. So they are meaning that you should specify that physical state. Are we together?
Yes.
And then since it is enthalpy of formation, when you're balancing the equation, you must make sure this is 1 mole of steam being formed, right?
Yes, teacher.
So how do you make this is 1 mole of steam formed? Look at the hydrogens here. There are 2, you put a 2 here. No, this is already 2. The oxygen is 1, you put a half here to make the oxygen atom 1. So since we are forming steam, our aim was to know which elements form steam. That is hydrogen gas and oxygen gas. But when you're balancing, I told you with enthalpies, we are always aiming at 1 mole of substance being formed for enthalpy of formation. Now, if I'm to expand this, this is a hydrogen-hydrogen bond. I think that one is very clear to everyone.
Yes.
Then oxygen normally oxygen normally bonds to oxygen by formation of a double bond. That's why here we have this half here, we bring it back here, and then we multiply it by the oxygen-oxygen double bond. Are we together?
Yes, teacher.
This is giving me water is here. In water, we have oxygen bonded to 2 hydrogen atoms. Is it okay, Benjamin?
Yes, it is okay.
So we have 2 oxygen hydrogen bonds, in other words, here. That's what is here in steam. Now, after knowing this, then I can go to my formula, which says enthalpy of formation of water is bond enthalpies of bonds broken. Whenever you're given these kind of questions where you see hydrogen bonds being given, this is the equation that works. Summation of bond enthalpies of bonds broken minus summation of bond enthalpies of bonds formed. So which bonds are broken? The bonds that are broken are those ones in the reactants. So the bonds that are broken are those ones in the reactants, which are here. We have the hydrogen-hydrogen bond plus I have oxygen-oxygen double bond minus the 2 oxygen-hydrogen bonds. Now here, the question is a bit tricky because they're asking us the oxygen-oxygen bond energy. This is what they're asking us. But we are given enthalpy of formation of the steam, which is here. Okay? And that is the enthalpy change occurring in this reaction. So that one, we know it, we put it here. Then the hydrogen-hydrogen bond energy is known. We don't know this, we leave it there as an unknown. It is what we are supposed to work and find out. This is what we are calculating. Then, this one is given, we substitute it there. Of course, we are multiplying it by 2 because there are 2 oxygen-hydrogen bonds here. Is that right?
Yes.
Now we make this the subject. When you make this a subject, this is already negative. This one will cross the equal sign, it becomes negative. That's why you start being subtracted. This was negative. When it crosses, it becomes positive. That's why you see it being added. Now, when you work out very well, this half will multiply this, the whole answer you get from this by 2, and you end up getting the oxygen-oxygen bond energy as that value in kilojoules per mole. Is that right? Is that clear so that I can proceed?
Yes, sir, you can proceed.
Inda, is that clear?
Yeah.
Okay. So we can now proceed to another question. Semanda, can you read for us that question? Hope you now see the screen.
Hydrazine reacts exothermically with hydrogen peroxide when used as a rocket fuel. The table below shows some bond energies. Here I have bond and bond energies in kilojoules per mole. I have
So
oxygen
we calculate
hydrogen
what?
bond. Calculate the enthalpy change for the reaction.
So this is a very tricky question, which is the last example about this. I want you to observe it carefully and see how to apply this formula. So I have hydrogen peroxide, 2 moles of it, reacting with hydrazine. This compound is called hydrazine, and this reaction occurs in a rocket, where the mixture of the two are used as a rocket fuel. Form water and nitrogen. Now, if I'm to expand this, it becomes this. The hydrogen peroxide, we have 2 moles of it, and this is how we could best write it. Hydrogen, oxygen, bonded to another oxygen, bonded to hydrogen. So those are the 2 hydrogens and the 2 oxygens. Hydrazine, we have nitrogen bonded to nitrogen, but each nitrogen having a bond to hydrogens, to 2 hydrogens. So this expansion helps me to know the bonds that are present therein. Water, we have already seen that this is 4 into the water. Nitrogen is always bonded to nitrogen by a triple bond. Is that okay?
Yes, teacher.
So if I'm to proceed, the enthalpy of this reaction is summation of the bonds broken, one enthalpies of bonds broken, minus the summation of the bond enthalpies of bonds formed that one wants to milk the mother. So bond enthalpies of bonds broken minus bond enthalpies of bonds formed, but it should be the summation of them. Now when you come back here, there are 4 oxygen hydrogen bonds. Is everybody able to know how the 4 oxygen hydrogen bonds come about? I want us to be very careful here. Is everybody able to know how the 4 oxygen hydrogen bonds come about?
From here you see.
Who else sees or who else
Yes.
doesn't see? Musime, do you see how the 4 oxygen hydrogen
I
bonds
also-
come about?
Yes, teacher, I can see it.
How about the 2 oxygen bonds?
Yes, teacher.
This is where I told you should be very careful. So the 4 oxygen hydrogen bonds are here. This is 1. Another one is here. Those are 2. But remember, the whole of this is multiplied by 2, so they become 4. Now the oxygen
Yes.
the oxygen bond is already here. It is 1, but this 2 multiplies this one to make them 2. Are we together?
Yes.
Now there are 4 hydrogen bonds here. It is this one, that's 1. It is a second one here. It is a third one here. And there is a 4th one here. Those are the 4 nitrogen bonds. Nitrogen hydrogen bonds, right?
Yes.
And then there is a There is a nitrogen bond. For it, it is 1. It is here. Everybody sees the nitrogen-hydrogen bond, right?
Yes, we can see it.
That's 1. So we add all of those ones together. Minus the bond is formed now. We have the oxygen-hydrogen bonds. We have the oxygen-hydrogen bond. We have this one here. It is 1. Then there is also this one here, which is the second one. So those are 2, but multiplied by 4, making them 8. Is that also okay?
Yes, teacher.
Then there is 1 nitrogen bond. So after understanding that concept, then you just substitute in and get your final work. The moment you understand this, just substitute in. The 8 multiplies everything is given in this table here, and then get your final answer by mathematics. Unit average kilojoules per mole. Is that okay?
Yes, teacher.
Is everybody understanding this?
Well, teacher.
Can I proceed?
Yes, teacher.
Okay.
But teacher,
Yes, please.
in the beginning, you said that the oxygen must be bonded with a double bond, but in this one, I'm seeing a single bond.
Oh, that is when it is in the oxygen gas alone. But here, this is molecule called hydrogen peroxide, right? But now, instead of the double bond being between the 2 oxygen atoms here, it would have been here. But instead of being there, remember the oxygen is now bonded to hydrogen. Each oxygen is bonded to hydrogen. That other single bond comes this side. You get it, Benjamin?
Yes, I'm getting you.
It only happens if the oxygen is only bonded to oxygen in the oxygen gas.
Okay, thank you very much.
That's where it is done like that. I think I can now proceed.
Yes, teacher.
Yes, sir.
This brings me to Hess's law. Hess was a man that studied a lot of thermochemistry some years back. After doing a lot of work, he discovered that there is a law that he could write as one sentence. He called it his own law, hence it became Hess's law. Who can read for us, how does Hess's law states like? How does it state like? Yes, Linda.
Hess's law states that the enthalpy change in a chemical reaction at constant temperature and pressure is the same whether the reaction is brought about in one stage or through intermediate stages, but depends on the initial and final states of the reactants and products.
Very good. Benjamin, how does Hess's law state like? Musime, can you be able to recall how Hess's law states like?
No.
Let's go back to the law. Here it is. It is a long law, a long one. It's a long sentence, but you should be able to know how you can state it. So these people discovered that when you carry out an enthalpy reaction, whether it can proceed by one reaction or you can do so many other reactions, does not matter how many stages you go through, but the law continues to emphasize that the enthalpy change of such a reaction depends The law continues to state that the enthalpy change of such a reaction depends on the initial and final states of the reactants and products. So Hess's law states that the enthalpy change in a chemical reaction at constant temperature and pressure, these conditions are very important, is the same whether the reaction is brought about in one stage or through intermediate stages, but it depends on the initial and final states of reactants and the what? And the products. With time, we'll get used to how that law can be stated. Can I go ahead?
Yes, teacher.
Linda, do your work. Linda,
Calculate the, yes, teacher.
do your work, Linda.
Calculate the enthalpy of formation of sodium chloride using the following data.
Part B.
Part B, for your answer.
Comment on the stability of sodium chloride and give a reason. Now you can be given this kind of data and you're supposed to use it in a question or in a calculation. So this is the data we are given. Who can tell me? This is now enthalpy changes, but given in equation. Which enthalpy change is this first one here? Who knows this enthalpy change?
Teacher, I cannot see it well.
How comes? And there is no way I can enlarge it further than this, because this is now full screen view.
Enthalpy of atomization.
Yes, this is enthalpy of atomization of sodium. Okay? Or enthalpy of sublimation of sodium. Are you now seeing well?
Yes, I can see, sir.
Now, which enthalpy is this second one here? You can tell me which enthalpy this is. Yes, Amanda.
It is bond dissociation energy.
Bond dissociation energy of what?
Of chlorine.
That's bond dissociation energy of chlorine, right? Then the third one is which enthalpy? Who knows the third enthalpy? Ian, can you try to guess which enthalpy is the third one? Ian is not there. Again, same and yes. Samanda, how do we call the third enthalpy?
It is first ionization energy. Therefore, first ionization energy.
Of what?
Of sodium.
Yes, that's first ionization energy of sodium. Mary, the fourth one.
The fourth one, first electron affinity of chlorine.
The fourth one.
Lattice energy.
Yes, this is lattice energy of sodium chloride. And then the last one is first electron affinity of chlorine. Now, you need that theory. If you don't know these enthalpies, it will give you a headache to work the question out. Now the question wants us to get enthalpy of formation of sodium chloride. The moment you see what the question wants you to calculate, you write that equation first. So the thing I'll write first is the equation for formation of sodium chloride. Sodium chloride is a solid. It is formed from sodium and chlorine. Okay, so the sodium is a solid, the chlorine is a gas. We multiply it by a half to get the sodium chloride. Are we together? So this should be 1 mole, as I've always told you. When we are looking at enthalpy of formation, we must make sure we form 1 mole here. What we do now, we don't have to put any other figure here other than 1. Ali watch Kenga. Linda Olichibona.
Yes, yeah.
Now the chlorine here is multiplied by a half, so that we get 1 chlorine atom, which should be here. But these states must be maintained that chlorine is a gas, sodium is a gas. So we don't balance these equations the usual way we balance the equations in inorganic chemistry, because this is enthalpy, we are aiming at 1 mole. Now after writing this equation, we are going to see how we play with these enthalpies here to come up with this equation. As we did in the previous lessons, we play around with these equations and go on crossing until we get my equation I'm interested in. For example, we have sodium solid here in this equation. Amongst these ones, where can I get the sodium solid from the first equation? I write that first equation with its enthalpy, right? Are we following?
Yes, teacher.
Now in this one, in the same equation, I have a half chlorine gas. Where can I get chlorine gas, which is Cl2? Not the Cl, but Cl2, it is in the second equation. So I write that second equation, but since this chlorine is a half, I multiply everything by a half. When I multiply everything by a half, this becomes a half. Even the chlorine here is multiplied by a half. So the chlorine that will be 2 now becomes 1. This is the one you're seeing here. And when you multiply this by a half, even the enthalpy is multiplied by a half. Am I clear?
Yes.
Teacher, about the second equation you are talking about.
About the second equation. So about the second equation, we have said, when I look at this, I've already got the sodium here from my first equation. I want the chlorine gas. The chlorine gas can only be got from this equation. But the whole equation is multiplied by a half, because the chlorine here is multiplied by a half. It's not 1 which is here. So I multiply that whole equation by a half. When I multiply it by a half, the half multiplies this, it also multiplies what is here. When I multiply this by a half, I remain with 1. That's why you see 1 here.
Yes, teacher.
When I multiply the equation by a half, even the enthalpy is multiplied by a half. Is that fine, Linda?
Yes, teacher.
Now, I've got my 2 equations, which I'm interested in. But in my, actually, what I can do next now to bring the equation in which there is sodium chloride, but on the reactant side, that I can ignore this first and come to this, because this is where I have the sodium chloride on the reactant side. I bring that equation, it's here, the way it is. It's multiplied by nothing, because even the sodium chloride is multiplied by nothing. You get it?
Yes, teacher.
Yes.
Then the other equation is like this one here, and this one are only brought to cross out the unknowns. For example, when I write this, its aim is to cross out this sodium that was in the first equation, so that I'm remaining with only these things I'm interested in. You get that? You get that?
We get it, teacher.
Now, this sodium ion is interested to cross this sodium ion too. Because I'm not interested in it, it's not anywhere in this equation. This chloride ion crosses with this chloride ion, which is gaseous. This electron crosses with this electron here, and I end up having the sodium which I want, which is here. I have the half chlorine which is here on the reactant side, then the sodium chloride on the product side. Have you understood the concept at this point? Members, have you got the concept at this point? Can I proceed?
Yes, sir, you can proceed.
Now, after getting that, I now want enthalpy formation of sodium chloride. I write an equation for it. The whole of this work here earns some marks. So you must show this working if you're in an exam. So you write this equation here, where you will get your answer. It's even half a mark. So I'm getting the enthalpy formation of sodium chloride, which I want. It is equal to this one, added to a half this one, added to this, this, and that. That's what is shown here. Substitute the answers there, do the mathematics. Finally, you get enthalpy formation of sodium chloride as that value. Are we together, members?
Yes.
Now, part B says comment on the stability of sodium chloride. Who can tell me what will be the comment? We are using the enthalpy formation here to make the comment. I remember telling you something about how you can know the stability of a compound using enthalpy formation in the previous topics. What shall we comment? Which comment shall we give?
I can try.
Yes, Benjamin.
It's more stable since it is having a high, since its enthalpy of formation is more negative.
Yeah, it is a stable compound. I'm just modifying your answer. It's a stable compound because its enthalpy of formation is negative. Okay. Or you can say it's a stable compound because its enthalpy of formation is exothermic. Am I clear? People, are you getting me?
Yes, teacher.
Yes. We're getting.
Come to another question. Linda.
Define the term standard heat of reaction.
Yes, who can define for us standard heat
Part
of
B,
reaction?
given.
Stop there. Stop there, Linda. Who can define the standard heat of a given reaction? That is what we looked at as we were beginning the topic. If you don't remember, please try to recall. You can be asked that question. Define standard heat of reaction. Now here, what is required is this enthalpy change. And here the enthalpies are given in words. So we must also try to make these enthalpies equations and finally play around with them until we get this equation. This will give us some good, to take us some good time to work on it, right? Yes. Now, when you look at this is enthalpy formation of magnesium chloride. How is magnesium chloride formed? By reacting magnesium metal and chlorine gas. The magnesium chloride is a solid in its standard state. I remember telling you that these states are very important. When you don't make correct states, you lose marks. Some people may now call this magnesium chloride aqueous. Anybody has a question? Now, some people may call this magnesium chloride aqueous. There is no way it can become aqueous. It is a solid because there is no water here anywhere. Am I clear? Am I clear, members? So now, when I proceed, this is the enthalpy we are talking about here. So that is the enthalpy of formation of magnesium chloride. It is here. So you have to transfer the words now into equations and then rearrange. So you write the equation of formation of magnesium chloride, the corresponding enthalpy which is given. The second one is now lattice energy of magnesium chloride. But with lattice energy, you should be very careful with the value given here. This is a positive enthalpy, and that means this is not lattice C. This is not lattice C enthalpy of formation. Rather, it's lattice enthalpy of dissociation. Because you see it is positive, it means heat is absorbed, it is endothermic. And when is heat absorbed? When there is bond breakage, when a bond is being formed. So now there, the enthalpy we shall look at is the lattice energy of dissociation, where there is breakage of the magnesium chlorine bonds. So the equation we write in that case is this one. However, if the lattice was negative, then we would begin with the ions forming the magnesium chloride. In that case, the lattice is endothermic, is exothermic. You get that point also? Members, are you getting me?
Yes, teacher.
Yes, sir.
Your perception determines my speed. If you're not getting me, that will take me slow. So the hydration energy of chloride ions implies that now I have chloride ions being hydrated. And that equation is written in this format. These are chloride ions forming aqueous chloride ions. So it's chloride ions in the gaseous state. That's what we call hydration energy of chloride ions. Chloride ions in the gaseous state, forming chloride ions in the aqueous state. Write that enthalpy also. Then I have enthalpy of solution of hydrogen chloride gas. That is what we are giving here in this equation.
Excuse me, sir.
Yes, please.
On the chloride ions, I haven't got you. You can pardon for me.
When I talk about hydration of chloride ions, I hope you remember the definition of hydration enthalpy. You remember it? The definition of hydration energy was the enthalpy change that occurs when 1 mole. Enthalpy change that occurs when 1 mole of gaseous ions. This is 1 mole of gaseous ions completely surrounded by water molecules. Form an infinite dilute solution with no change in pH. Okay? So that's what we call the enthalpy of hydration. We have chloride ions that are gaseous. We completely surround them with water, form aqueous chloride ions. That's what we call enthalpy of hydration. Mike, I mean, you're not responding.
I'd say you're clear. I've got you.
Now, when I go to enthalpy of solution of hydrogen chloride gas, it's the hydrogen chloride gas now forming hydrochloric acid. That means putting hydrogen chloride gas in water. Then we have enthalpy of formation of hydrogen chloride gas. This is the trickiest part. It is here. We have hydrogen reacting with the chlorine to form hydrogen chloride gas. I told you when you're balancing the equation, you must make sure this is 1 mole. There shouldn't be any figure here in enthalpies. That's what we mean by enthalpy of formation. So to come to that, you must make sure each of these atoms multiplied by a half. You multiply each by a half, then you come up with this enthalpy here. Then hydration energy of magnesium ions is here. It is the magnesium ions in their gaseous state. That should be very important because that's what defines hydration energy. Enthalpy change that occurs when one mole of iron is in their gaseous state is completely surrounded by water molecules, form an infinitely dilute solution with no change in pH. Now, have you got this first part here of deriving the equations from the words and their corresponding enthalpy, so that we proceed now? I think this is very clear. Is that clear, members?
Yes, teacher.
If that's clear, now we have to play around.
Yes, sir.
We have to play around with these equations so that we derive the equation given here. The equation is what we want. This one is what we want, but from these. Now, I must first of all ask myself, where shall I get the solid magnesium? The only way I can get the solid magnesium is this first equation. I write it here. With its enthalpy, I leave it there. Is that okay?
Yes, teacher.
Then how shall I get the aqueous hydrochloric acid? Because this magnesium reacts with aqueous hydrochloric acid. The only way I can get aqueous hydrochloric acid is from this equation here. This is where I have aqueous hydrochloric acid. You see it?
Yes.
So, but when I look at this, the hydrochloric acid, when I look here, the hydrochloric acid is on the reactant side. So I must change this equation and I reverse it such that the hydrochloric acid begins this way. And then the hydrogen chloride gas is turned this way. And after reversing it, I also go ahead and multiply it by 2 because this hydrochloric acid is multiplied by 2. So that's the purpose of this 2 here. Now the two things I've done are summarized here. I reversed the equation, so that makes it negative. Even this value is made negative. Although it was negative, it's multiplied by another negative. Then I multiply the 2 because I have reversed. In other words, I multiply the whole equation by negative 2. Why? I've reversed it and I've also multiplied it by 2. Has that been got, members?
Yes,
It's
teacher.
understood. Yeah.
So if that is good, then I look at the magnesium chloride. The magnesium chloride is aqueous and it is on the product side. Where do I have magnesium chloride aqueous and on the product side? I don't have that anywhere. I don't have the magnesium chloride aqueous and on the product side. So that equation, I can leave it for now. It will come automatically. What you don't see, you ignore it. You will see how it comes generally later. How do I get hydrogen gas on the product side? Hydrogen gas on the product side is got from nowhere. The only way I can get hydrogen gas will be on the reactant side. So I'm going to use this equation, but reverse it so that the hydrogen gas goes to the product side. How do I do that? That equation is where? Do I have it anywhere? Yes, it is here. I write the equation here. So I write the equation. This is the equation I've written. I reverse the equation such that the hydrogen is on the product side and also multiply the equation by 2 so that my hydrogen has 1 here because there is a 1 here. So the only way I can make this one is multiplying the equation by 2 and also reversing it. That's why you see it here. It's multiplied by 2 throughout. Their halves disappear. There is a 2 here and also reversed. That's the essence of this negative 2. The equation is reversed and everything multiplied by 2. Are we together?
Yes, teacher.
Now the other equations are brought in to cross whatever I don't need. For example, in this equation, I had the magnesium chloride here, which is a solid. How do I make sure it is cancelled? Because the magnesium chloride I have here is aqueous, not solid. So now I can make that crossed by bringing this equation where I have the solid this side. I write it here. So the solid will cross with that solid. I'm not interested in it. My equation here has no chlorine gas. How shall I make sure the chlorine gas here disappears? I write an equation in which chlorine gas is on the product side, which is this one. Already there, the chlorine cancels with that one. So the things come automatically. The moment you write down the equations, everything cancels automatically. You add up each of the things here and come up with a final equation and then the final answer. I hope you'll give that some good time in your free time. Have you got the concept? So enthalpy of reaction here equate to each of these added together with their 2's multiplied on them. Okay, and then substitute in there, you get the final answer. I hope that is also clear. Any question? Is there any question so far? Hey, Cheza, you've understood everything, not so. So I proceed here. What we call a Born-Haber cycle. Please take time and try to go through that work there. Now this brings me to what we call enthalpy cycles. Linda, can you read for us here?
A Born-Haber cycle is a technique of applying Hess's law to the standard enthalpy changes.
Linda,
Born-Haber cycles are used to calculate enthalpy changes which are difficult or impossible to evaluate directly. These include theoretical values of lattice energies, electron affinities, and enthalpies of formation. The only energy term in the cycle that cannot be measured experimentally is the lattice enthalpy, and the cycle enables its value to be determined. The cycle can be an energy level diagram or enthalpy cycle.
Very good. So you're going to look at Born-Haber cycles and energy level diagrams. The Born-Haber cycle is a technique for applying Hess's law to the standard enthalpy changes, which Hess's law we have already seen. These cycles are used to calculate enthalpy changes which are difficult or impossible to evaluate directly or to be got by experimental means. So normally Born-Haber cycles or enthalpy cycles or energy level diagrams are used to get lattice energies, electron affinities, and enthalpies of formation. That's always their major aims. And the only energy time that cannot be determined experimentally is the lattice enthalpy. Although they can determine all the three enthalpies I've seen above, the commonest one they normally ask you from the energy diagram is the lattice enthalpy. Which terms are used in enthalpy cycles, Linda?
Standard enthalpy of sublimation.
Yes.
Standard enthalpy of ionization.
Yes.
Standard bond dissociation.
Those are the commonest ones, including three more others. Which ones are those?
Electron affinity.
Mm.
standard lattice enthalpy, standard enthalpy of formation.
So in Bonn-Haber cycles, you'll be meeting these enthalpies here. These are the commonest ones. You'll be meeting enthalpy of sublimation. You'll be meeting enthalpy of ionization. It is very hard to draw an enthalpy cycle and these ones miss. Bond dissociation enthalpy, sometimes it can be given as atomization. So for you, your aim is to know that bond dissociation is always twice atomization, electron affinity, then lattice energy and enthalpy of formation. Can I proceed?
Yes, sir.
Which points should we note when drawing Bonn-Haber cycles or enthalpy diagrams? Samantha, which points should we note? This is where you go wrong.
The cycles should have well-balanced equations.
So although these are enthalpy cycles, there are always equations written. Indirectly, there are chemical equations written, but within a cycle. So you should always have those equations well balanced. If they are not well balanced, the whole cycle, if the cycle has a lot of equations, but only one is not balanced, then the whole equation becomes wrong. What next? Frederick, what next? Frederick, I'm not getting you. Is it your network?
Ions should have correct charges.
The ions should have correct charges. Let me emphasize this. This is what we mean here when we say this. You have already seen this. Somebody may write this ion here, chloride ion, and then call it aqueous. Yet he's talking of hydration energy. So for hydration energy, they are gaseous ions forming aqueous ions. Then somebody talks of hydration energy of magnesium ions, atenawandika magnesium ions, aqueous. So you must be very careful with the chemical symbols in these enthalpies. If the chemical symbols are wrong and the charges are wrong, you lose marks. So the charge here on the magnesium ion is +2, you make it in +1, you lose marks. If it is +1 for fast ionization energy and make it +3, still you lose marks. Yes, what is the third point we should note?
The chemical symbols of the elements must be correct.
Then what next?
State symbols must be shown and should be correct.
State symbols must be shown and also should be correct. Then the enthalpy values must be, go ahead.
The enthalpy values should be shown along with the reactions they represent in the cycle.
Yes. And then what next?
For the energy level diagram, it's important to consider the ranges between any two energy terms.
You're going to see that later. So you must have those points understood before you draw an energy level diagram. Okay. Narima, can you read for us here? Narima again.
Energy level diagram. An energy level diagram shows the energy changes in the order they happen. Endothermic or positive enthalpy changes are shown upwards, and the exothermic or negative enthalpy changes are shown downwards. The diagram also must show well-balanced equations with state symbols inclusive, and the energy changes must be labeled.
Very good. So an energy level diagram shows energy changes in the order they happen. So endothermic, all positive enthalpy changes are shown moving upwards in the energy level diagram. Then those which are exothermic or negative are always shown moving downwards, as we shall see. The diagram still must show well-balanced equations with the state symbols inclusive in those diagrams. We have a question here. So the data is normally given as you see in this question here. The way you see this question is always how the data is given. Okay. So given the data as you see here, and then you're asked to draw an energy level diagram or do some questions. So they are saying you're given the following data. The first one is standard enthalpy formation of aluminium fluoride. You read through all of them, then they say, draw an energy level diagram for formation of aluminium fluoride. So the moment you see draw an energy level diagram for formation of aluminium fluoride, this is what you do. The heading is not so important. Draw such a line, the way you see this line here. And when you draw this line, show arrows up and down, showing that there are enthalpies moving up and enthalpies moving down. Now, slightly below, not in the middle, but slightly below this line, put your first line as shown here, and put there the 0 level. Put there the 0 showing that that is 0 kilojoules per mole, and label that axis as potential energy in kilojoules per mole. Are we together?
Yes, teacher.
So after you've done that, you've drawn this line, you put arrow up and down, you put a 0 here, you've labeled this. The first thing you do is to look for the binomial nabe all of these ones that are given to you. First of all, look for enthalpy formation. That's the first thing you look for. Look for the value for enthalpy formation and write the equation for enthalpy formation. Formation of aluminium fluoride. Now, how is aluminium fluoride formed? Aluminium fluoride is formed this way. We have aluminium metal. It is a solid reacting with fluorine. Are you seeing the equation I'm writing?
Yes, sir.
Are you seeing the equation I'm writing?
Yes, teacher.
So write this equation. This is aluminium metal reacting with fluorine. Fluorine is the atomic. This gives us aluminium fluoride. Excuse me, I'm writing using a pen and I've not yet learned how to write. Aluminium fluoride is AlF3. Because aluminium has valence 3 and fluorine has valence 1. This is a solid. Now, when we talk of formation, you must make sure there is a 1 here, nothing else, to help you balance the equation. So what value shall I put here to balance this equation? Who can tell me? Which value do I have to put here to balance this equation?
3 out of 2.
Is everybody knowing how the 3 out
3
of
out of 2.
So everybody is aware of how the 3 out of 2 comes about, right?
Yes, sir.
Teacher.
Oh, yes, please. Narima, what are you saying?
I'm seeing where the 3 out of 2 is coming from.
Okay, thank you for seeing. Very good, girl. So you put 3 out of 2 here. Now, the moment you know this equation, you've done it as side work, come here. The reactants, write them on this line. That's what you see there with their states and the symbols written well. Then the product, which is aluminium fluoride, draw another line at the bottom, write it there. Put this arrow moving downwards, show that that's delta enthalpy formation of aluminium fluoride, its value, which is negative. Enthalpy formation in this case is always negative. Why do we put the arrow going downwards? I told you negative enthalpies move downwards, the positives move upwards. Are we together up to that point?
Yes, sir.
Now, after knowing that that is how we do enthalpy formation, the first thing you do is now to consider the metal. Which metal here is aluminium. So the metal here is aluminium. Aluminium is solid. No one. The first thing you'll do is to move upwards and draw another line here. Then you atomize this aluminium. Remember, it is a solid. The first stage it has to undergo is to form aluminium gas, which we call the sublimation or atomization. Are we together?
Yes, teacher.
Yeah.
So you draw a line moving upwards, make the aluminium a gas. As you maintain the fluorine, don't do anything on this fluorine, maintain it with its 3/2 as you move. So you are writing equations on lines, but we are still dealing with aluminium. You maintain the 3/2 fluorine here. Musime, can you mute yourself? There's some noise I'm hearing, which is... I think that's fine now. You unmute yourself if you want to say something, ask a question or give an answer, so that we minimize the noise. So the aluminium solid now becomes a gas, and that is enthalpy of atomization, which is given here. Remember, these things sometimes they may not be given in order. So for you must know how the steps move and know which enthalpy you write first. Can I proceed?
Yes, teacher.
Now, after atomization of fluorine, aluminium has formed aluminium gas. This aluminium gas now is going to undergo what we call fast ionization energy. So that's the enthalpy right here. Make it fast ionization energy, write the aluminium ion here, gaseous. And then write the value of the fast ionization energy. So you see now how they would confuse. They give you bond dissociation energy of fluorine, which you must not use now, but you must first of all use the fast ionization energy. You must know how the enthalpies follow each other in the cycle. So these are all positive. That's why we are keeping on moving upwards. So enthalpy of fast ionization energy of aluminium is this value. Write it in the cycle. Don't put the units here because you must have put them here as you labeled on this line. Ian, are you getting me?
Yes, sir.
How about Benjamin?
Yeah, I'm getting you.
Okay. Now, after writing that, we proceed. We now go to the second. Remember, the aluminium here uses a valence of 3 to bond to the fluorine. That means we must go up to the third ionization energy of aluminium to attain that valence of 3 we are talking about. If it was calcium fluoride, then we would move up to the second ionization energy because calcium bonds with the fluorine using a valence of 2. So for calcium, we would go up to the second ionization energy. Now, we go to the second, and always the data is given to you to simplify your work. So this is the second ionization energy. We make the third ionization energy, still dealing with aluminium. That's why we end up here. But this fluorine, we must maintain it as 3/2. For it, we are not playing around with it. So it's maintained the way it began here as we move upwards. We don't change anything for fluorine. Are we together?
Yes, teacher.
So it goes with it 3/2 until we reach the third ionization energy of aluminium. That's when aluminium is first dealt with. So after we have completed the thermochemistry of aluminium, now we go back to our fluorine. That's why you see now the arrow is here. We have now begun the fluorine. Are you getting me?
Yes, teacher.
So the fluorine, which is a non-metal, will undergo its first enthalpy change, which will be now the bond dissociation. How do we do bond dissociation of fluorine? Fluorine to bond dissociate, this is what we would be meaning. Let me get my duster here so that I can get some space where to do my work. So when I talk about bond dissociation of fluorine, this is what I mean. These are the enthalpy changes that fluorine will undergo. What's really happening? Something disturbing me here. So the fluorine is written like that. It will first of all undergo dissociation. When it undergoes dissociation, it forms 2 fluorine atoms. So that's why I begin defining these enthalpies when we are beginning. So that's the fluorine gas. That is not clear, but take it to be gas. So fluorine gas is forming 2 fluorine atoms. That is bond dissociation. Now this fluorine will go ahead to make fluoride ions, which fluoride ions are still gaseous. So we put a negative here, and the equation must be balanced. There is a 2 here, so we have to put a 2 here. Why do I do this? It guides me how I'm going to deal with the fluorine on the cycle. Is everything okay up to this point? Members, are you following?
Yes, teacher. Yes, teacher.
Shamire, obitegeera bino byenkola?
Yes, teacher.
Now, when I deal with this, that is the principle that I know. But here in the equation, my fluorine is multiplied by a 3/2. You see, it has been coming with a 3/2, which began from here. So what I'm going to do is to come here, and I also multiply my fluorine with a 3/2. That's going to change everything. When I put a 3/2 here, which is in the equation, this will also be 3/2. And that 3/2 will cancel everything here. This 2 will cancel with this 2, such that here I remain with the 3. You get that?
Yes.
And this one will be multiplied by 3/2, which 3/2 will cross out the 2 that is already there, and then I remain with a 3. Have you got the concept?
Yes, teacher.
Now we come back here to our cycle here. Now from here, the 3/2, since here I'm given bond dissociation energy of fluorine, when I wrote it initially, there was a 1 here. That's what we call the bond dissociation energy. When I put a 3/2 here, then I also multiply the bond dissociation energy by 3/2. Okay? So why I did this, I was trying to figure out this 3/2 comes about here. So this value here, in other words, in simple terms, when you write this equation, this 3/2 here multiplies the bond dissociation energy, and you must multiply it by 3/2. You must not always forget such a thing in the cycle. Then it forms fluoride ions that are gaseous, which are 3. We have seen how the 3 fluoride ions come about from here. We have seen how they are generated from here. So the 3 fluoride ions are already here with us now. And then they have to undergo another enthalpy change, which I've already shown you, which is the first electron affinity. The first electron affinity. And this first electron affinity, you see that for it, it is negative. It is moving downwards in the cycle. So at this point, that's why you see me moving downwards. Remember, I reached the aluminium 3 here. So the aluminium I maintain where I stopped. Now I've begun on the fluorine, which I've just changed here. Since this next value here, the electron affinity is negative, now I have to move downwards. And for that one, I must multiply it by this 3 here. This 3 must multiply the first electron affinity. That's why you see it multiplied by 3 as I substitute here. After reaching this point, I've now got the aluminium ions gaseous and fluoride ions gaseous. In this cycle, I want you to note this. In this cycle, there shouldn't be anything like a aqueous state. Doesn't appear anywhere in this cycle. In the cycle, there is only solid. The states that appear there are normally solid, gas, sometimes liquid, but normally solids and gas states appear in this energy level diagram. Now, after reaching this point, I draw a line, move downwards, and this enthalpy here, I don't know, I call it lattice. Have you understood me up to that point, members?
Yes, teacher.
Yes, teacher.
Is there anybody with a question? Musime, are you getting me?
Yes, teacher, but I have issues with the network, I think, because at times I've not been hearing you. I think it is my own network. I have to check it out.
Okay, sorry for that. Now, so after drawing the energy level diagram, that one will always give you some 2 marks or 2.5 marks. It depends. It can even be 3. It depends on the marks that are given to it. Now, when you come to, after drawing that energy level diagram, you're required to calculate the lattice energy of aluminium fluoride. How do I get the lattice energy of aluminium fluoride? Now I use the S0. This is the enthalpy they want here, the lattice energy. So what do? I say that enthalpy of formation, which is here, this enthalpy here, is equal to, I add this one, this one, this one. You see how this road moves, this cycle moves. So I say that my enthalpy of formation will be equal to this, added to this, added to this, added to this. added to this, added to this, added to the lattice. That's where this equation comes from now. Are we together?
Yes.
So that's where that equation comes from. Now, after knowing where that equation comes from, please write it down and get that half mark always. After writing the equation, do the substitution of the values. Those ones that are multiplied by some figures, don't forget those figures. Actually, the multiplication always comes with the lattice, I mean with bond dissociation or atomization and then electron affinity. That's where the multiplication comes in by a certain figure. Substitute that. Then after substituting that, make a lattice subject, lattice energy the subject. So you make your lattice energy the subject. When you make it the subject, it will turn this side and the formation goes the other side. That's why you see this. This value is already here. Now when these ones comes this side, this one is becoming negative, this one become negative, 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 negative here. That's why you see the whole of this. Get your final answer by doing the mathematics very well. Am I clear, members?
Yes, teacher.
So that's how we get lattice energy. And after getting the lattice energy, you can now calculate the hydration energies. How do you calculate the hydration energies? We saw that previously. Because you've got the lattice, you can now use the hydration energies that are given. Yes, Samantha, what's your question?
My question is about why is this value of lattice energy is negative?
This value is negative because you look at this. These are ions that are forming a solid.
Oh, yeah, I forgot.
Ions that are forming a solid. So energy is given out. That's why it is negative.
Okay.
Even the arrow would tell you, because the arrow is moving downwards, it would tell you why this is negative. Automatically it should be negative if your arrow is moving downwards like that. So can I proceed?
Yes, sir, you can proceed.
So if you look at this, we are now going to calculate hydration energies. No, we are given the hydration energies of aluminium ions and fluoride ions. They want us to get enthalpy of solution of aluminium fluoride. So now, after knowing that, so I want to get enthalpy of solution of aluminium fluoride. I'm aware that aluminium fluoride has 1 aluminium ion and 3 fluoride ions. Okay? It has 1 aluminium ion and 3 fluoride ions. So before I get enthalpy of a solution, I must get its enthalpy of hydration, which is given as enthalpy of hydration of the 1 aluminium ion plus thrice enthalpy of hydration of 1 fluoride ion, because I have 3 fluoride ions here. That's the only trick there. So multiply the enthalpy of hydration of the fluoride ions by 3. And then you must also know that these enthalpies of hydration are always negative, such that you put the negative sign on them as you're substituting here. So when you put the negative sign on them, you get enthalpy of hydration of the fluoride, aluminium fluoride. Then you get your enthalpy of solution by getting the lattice energy plus the hydration you have got. Substitute there, the lattice here. The lattice here is negative. The lattice here is negative. But when you're substituting it in here, substitute it in as positive. Am I clear?
Yes, teacher.
So the lattice is negative, the value you've got here is negative, because that's energy of formation of the aluminium fluoride from the aluminium ions, which are gaseous. But here, when you're substituting it, substitute it as positive, because here you're talking about last energy of dissociation. For substance to go to dissolve in water, it must dissociate. So here you substitute it as positive, the hydration as negative, and then get the enthalpy of solution. Are we together?
Yes, sir.
I think I've explained this example in detail. We go through one other example because it's already past time. We haven't completed the topic. Maybe we shall complete it in the next lesson. There are only a few things remaining still about Born-Haber cycles. I think you're already tired. Don't so?
No.
Not sure, you are not.
Who is not tired?
Me.
Malinda,
If I'm not tired.
Malinda, aren't you tired?
I'm not tired.
Now on GAO. I thought at least I thought you would say you were tired. Then
Master,
we go to
proceed.
the lesson. Okay, let us look at one more Born-Haber cycle. Here we are. And this is the last one we are talking about. Here I'm going to be very fast. Here I'm going to be a bit faster because I've taken some good time on the previous one. They are telling you to use the data below to calculate the lattice energy of. This is an energy level diagram still. They are telling you to use the information given to calculate the lattice energy of calcium oxide. What will you do? It's what you're gonna do. So here what you will do, I told you draw this line, put the potential energy there. In kilojoules per mole. Somewhere below put a 0, draw a line there. Then you should know how calcium oxide is formed by the equation, such that you don't make mistakes. Calcium is a solid. It is formed by reacting it with oxygen. It's formed by reacting the calcium with oxygen. So the oxygen is here. And we are forming calcium oxide. In calcium oxide, each of the elements has valence 2. So this is the solid calcium oxide. Now this equation must be balanced with the one here, nothing. You shouldn't put any figure here. How do you make that possible? You can tell me, how do I make that possible?
Teacher. We put a half on oxygen.
So we put a half on oxygen.
Oxygen.
So there is a half there. Now after knowing this, come and use the same idea here. Write the calcium oxide, calcium solid, and a half oxygen gas here. Draw an arrow. Write the calcium oxide there. And put that value there. Did you get it? You get it, members? Do I proceed?
Yes, teacher.
Proceed.
After doing that, start playing with the calcium. The first enthalpy, as I've already told you, is the enthalpy of atomization of calcium, where the solid calcium is becoming gaseous calcium. So we have already dealt with this one. The next one is now this one. You see now these ones are not in order, but you must know which order you must follow. So I now form atomization of calcium, which is a solid, put it there. Now here we shall go up to the second ionization energy of calcium because calcium has a valence of 2. So after atomization, we look at first ionization of calcium, which is here, calcium plus gaseous. Go to the second ionization of calcium, calcium 2 plus gaseous. Stop there with calcium. Begin looking at the oxygen. Remember I told you with the oxygen, you go on maintaining these halves here. You go on maintaining them. Now with oxygen, we begin at it at this point. With oxygen, the first thing we shall have to look at is to know what happens. Oxygen is diatomic. It must first of all form 2 oxygen atoms which are gaseous. Is that clear?
Teacher.
Then it goes ahead to form 2 oxide ions which are gaseous. Then it goes ahead to form 2 oxide ions because we must always make sure everything is balanced. Let me plug in my computer and then we proceed. So this sequence here must be understood for oxygen. Why do I go up to this level? Because in the calcium oxide, we have the calcium ion and the oxide ion. That's what we have there. Here we have the calcium ion and the oxide ion, 2 minus. These are the ions that are there. So for calcium, we go up to the second ionization energy, and for oxygen, we go up to the second electron affinity. So this value here is what we call the bond dissociation. And that bond dissociation is not multiplied by any figure. However, since our oxygen we have been moving with here has a half of it, this half we got it after balancing the equation. Then when I put a half here, even the bond dissociation energy is multiplied by a half. Even everything here is multiplied by a half. So the whole of this will give us a 1. Even here when I multiply by a half, it gives me a 1. Even here when I multiply by a half, it gives me 1. Have you understood that concept? Are you getting me, members?
Yes, teacher.
Now, when I multiply everything by a half there, that's why you see that here my bond dissociation was multiplied by a half. Then after multiplying the bond dissociation by a half, I had the half oxygen gas being converted to the oxygen atom gaseous. Now I got what we call the first electron affinity. I've finished this. I go now to the first electron affinity of oxygen. Remember, it's negative. So that one we shall move down. That's why the arrow is moving down, because it is negative. And that first electron affinity is not multiplied by any number, because remember we saw that everything here becomes 1. So remain it with it as a 1. This one here is multiplied by a 1. Then the second electron affinity for it is positive. So after moving downwards, we again move upwards for the second electron affinity of oxygen, which is now positive. The calcium we erode at the level of it being a calcium ion, so we go on maintaining it in both points. Now here, the first electron affinity, the oxygen gaseous atom, has become the oxide gaseous ion. For the second electron affinity, the oxide gaseous ion is becoming negative oxide gaseous ion. So that's how we draw the Born-Haber cycle. After reaching this point, the last value, of course, is this line here that moves downwards to show us the lattice enthalpy. Have you got me, members?
Yes, sir.
Yes, when you're doing a lot of practice, you'll understand. Those with the physical chemistry book has a number of questions that you can try about these energy level diagrams. Those without, I'll be sending these notes, but these notes are not so elaborate. The books have so many questions you can try out to see that you understood this. Now you do as we did in the previous example. You equate the enthalpy of formation here to this value, added to this, 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 added to this. Then you make the last the subject and come up with your final answer. I hope I'm now very clear.
Yes, teacher.
Yes, teacher.
Tusome, sir.
Hey, Ali, is everything okay with you?
Teacher, I thank you so much, but the problem today I had it was network best. I will check out the network.
Sorry. How about Benjamin? Benjamin, is your network fine?
Yeah, it's trying, but it is not very fine.
Okay. Is it now raining in Imbarara?
No, it isn't.
Okay, we assume it will be very fine sooner than later.
Yeah.
I think
that's true.
you people have understood everything today.
Mm-mm.
I think we understood everything today. Ali will talk with me via WhatsApp. I think if you don't have my WhatsApp contact, Benjamin will give it to you.
Teacher, you're talking to me?
Yes, Ali. You will talk to me after the lesson.
And I've been not hearing. After, yes.
You talk to me, we discuss something. Then the others, I hope you have no issues.
Teacher, for me, I'm having something to say.
Yes, please.
And it's like a suggestion on behalf of other class members. I was of the view, or I was suggesting that at least you rob us another lesson, even if it is very short, but we have like 3 lessons a week at least. Yeah, even if it is very short, but we have 3, at least we can be able to push something.
I have a tight schedule.
I
have a tight schedule. This is not the only Zoom platform I'm running. I'm running about 5 Zoom platforms, and sooner there is another one still I'm beginning. But we shall see if that is possible. I'll try to schedule some other lesson. But that means it will have to be in the afternoon hours.
Okay, there is no problem with that. Any time that is convenient for you, for us, we shall be there for that.
Okay then.
And then what about in the morning, like tomorrow in the morning before 9?
Before 9, I'm doing other things. Actually, that morning I was from 6 to 9. I don't have any lesson there. I'm always doing some other things.
Oh.
All right.
You try to rob us another lesson. It's what we are just requesting for.
That's very fine. We shall see. For this topic, I'm remaining with only about 4 diagrams. I think we shall complete them in the next lesson, and then prepare any issues we have about this topic. The next lesson, we shall be completing it to the detail, of course, with any issues you have about it, and then we begin physical equilibrium.
Yes, sir.
Right. Nice time. Mwebale munonga.
Anyway, teacher, webare.
Thank you, teacher, for your lesson.
Okay.
Thank you, teacher.
You're welcome.
Thank you, teacher.